Right?
Yeah.
Okay, great. So I'm very happy that we managed to get Noah to speak to us in person. And yeah, looking forward. Woo!
Yeah. Thanks. Yeah. So thanks everybody for showing up on an irregular day. I booked this visit like 2 months ago, and Ivry very kindly asked me to stay for the whole week, which she had amazing foresight to predict that there would be this storm. So yeah, so thanks for having me. And I'm going to talk about agreement testing, which I know there are some people here, maybe half the people here are like extreme experts on, and its relationship to these objects called coset complexes, and in particular, how you can get agreement testers from coset complexes. This is joint work with my advisor, Ryan O'Donnell at CMU. Okay, so I'm going to tell you about the agreement testing problem for those of you who haven't seen it before. So suppose you have a hypergraph. Like in this case, I drew a cycle, and it's a 3 uniform cycle, but you really should think of it as, I don't know, a k uniform hypergraph where k is some large constant. And suppose you have a coloring of this hypergraph. So this is a coloring of the vertices to each vertex. In this case, it's just a 0, 1 coloring, which I've represented as green and purple. And you have this single global coloring of all the vertices in the hypergraph. You can make this into a bunch of local colorings where each different edge in the hypergraph has just a coloring of the vertices that are in that particular edge. So like, for instance, this vertex 12 is in 2 different hyperedges. So there's sort of 1 copy of this hyperedge and 1 copy of this hyperedge, and they each think that vertex 12 has color green. Okay, so we can think about when can you reverse this process? Or if you're given a family of these local colorings where every hyperedge like has an opinion about what its coloring is supposed to be, can you determine a single global coloring that's consistent with all of these sort of local colorings? And okay, it's not hard to see that this is true if and only if, when you look at all the overlaps between different hyperedges, the 2 hyperedges have the same opinion about what every vertex should be. If they overlap on that vertex, then you can sort of glue all of these local views together into one single global view. Okay, so I guess that's what I wrote here. And so the question which agreement testing is interested in, oh, sorry, I wrote like, this is the gluing. So like this hyperedge is consistent with this hyperedge in the sense that they agree on their overlapping vertex, and therefore you could sort of glue them together and everything sort of links up nicely. So the question which agreement testing is concerned with is, what if you have some hyperedges which don't agree on some colorings? So this is an example, like these hyperedges agree, but then these 2 hyperedges like are in a dispute because they have a different opinion as to what the color of this vertex should be. And an agreement tester, I'm only going to define informally in this talk because our work is a little bit, I guess, upstream of that. But an agreement tester, informally, what it says is that if you have a lot of agreeing overlaps, then you have some coloring which is maybe not a perfect coloring. You know, it can't possibly agree with every hyperedge if there are some disagreements between the hyperedges, but you want some sort of like quantitative relationship between the amount of sort of agreement on the overlaps and then the amount of agreement with this global central coloring with the local colorings. And there's been many works on this. So like, for instance, I think Irit and Avi and co-authors had results saying that if this graph were the complete hypergraph, then it has good agreement testing properties. And I guess I should say that you're always interested in designing hypergraphs that also have good sampling properties. So the cycle maybe looks like a good agreement tester in this sort of, in the sense that if you have a cycle and you have lots of overlaps, then you can expect a good global coloring, but the cycle is a terrible expander. And we're interested in making agreement testers in this sense that are also good expanders. And the goal of a very long line of work that sort of culminated a few years ago was to make sparse hypergraphs that have similar good agreement testing properties to the complete hypergraph. Does this make sense? Okay. Yeah, so I should say the cycle is maybe a misleading example because it's a terrible expander and you want a good expander. Okay, so these great agreement testers, where by great, I mean that they're sparse and they also work in sort of the full parameter regime of all the different possible overlaps, you sort of get a different guarantee. These objects were shown to exist modulo the existence of some other objects called great high dimensional expanders. And great has a technical meaning here that I'll say a little bit later in the talk. And there were two papers that had a similar implication. One of them is by Yotam and Irit. And then following up on this, there were constructions of these great high-dimensional expanders based on some construction due to Chapman and Lubotzky, and this was another paper of Irit and Yotam and Alex Lubotzky, and another paper also at the same time. And so using these great HDXs, they could then plug into these implications and get these great agreement testers. And then following up on this, last year, there was another paper by Bafna and Minzer and Vyas that showed using these great agreement testers, you could get great probabilistically checkable proofs. And here great also has some technical meaning like quasilinear length and constant or low constant soundness. And this has some implications. For instance, they prove ETH hardness of approximation that is better for some problems. And somehow these agreement testers were originally motivated by applications in PCPs. I think people have known for like 30 years, maybe almost, that good agreement testers are related to good PCPs, but they're also sort of independently interesting mathematical objects. Okay. So the main goal of our work was to plug in a different object here at the bottom of this sort of path and plug in a different object and show that this object is a good HDX and therefore get good agreement testing and therefore get good PCPs also from this object. And in particular, as I said, Yotam and Irit's paper with Alex Lubotzky and also this other paper used a construction that was based on this construction of Chapman and Lubotzky. And this construction, I do not understand. I'm a computer scientist and not a mathematician. And the construction, I think, involves some number theory and algebraic group theory. And this is a paragraph taken from the other paper about what the construction is. I don't understand what this paragraph says, although I know that there are some people at IAS who do understand this paragraph. So this is how I feel about this paragraph, which is I don't understand what the construction is. And in this paper, we analyze an alternative construction, which is due to Kaufman and Oppenheim. And one very nice property of this construction is that it's completely elementary. So I can, in fact, will give a constructive proof of the elementariness by telling you what the object is in this talk. And it also has some nice technical properties, like it's very symmetric, it's more symmetric, and it's also super explicit. So it's a hypergraph or a simplicial complex, and if you put in a vertex, there's like a super fast algorithm that tells you what the complex looks like at that vertex, like what are all the hyperedges that are touching that vertex and so on. Okay, and the main theorem of our work is that all of these agreement testing and PCP properties, which were shown to hold for this Chapman-Lubotzky complex, also hold for this KO complex. Okay, does that make sense? Okay, so I think before talking about how we actually analyze the HDX properties, I'm going to give you a little bit more setup because it will make it a little easier to understand why we're studying the things that we do later in the talk. So this KO complex is an example of this broader construction called a Coset complex. And a Coset complex is a very nice object. It's a way to define a simplicial complex given a group and then some subgroups of that group. Okay, and by the way, if you're not familiar with this like rank K simplicial complex, you can just think of it as a K uniform hypergraph. Maybe if you call it a simplicial complex, that sort of means you also include all of the sub hyperedges that are within the K size hyperedges, but it doesn't really matter. And this Coset complex has some nice properties. It's super symmetric, and also understanding the structure of the complex in terms of its expansion or its connectedness is very closely related to the group theory of the group that you use to define the complex and the subgroups that you chose to define the complex. And there are various constructions of these high-dimensional expanders using Coset complexes. So this started with this work of Kaufman and Oppenheim. This is the type of complex which we study in our paper, where the group that they use is the group of all determinate one matrices over a finite field. And then there have been various follow-ups on this that show sort of for bigger and bigger classes of groups, you can instantiate this construction and also get some good high-dimensional expansion properties. Okay, but we're just studying this sort of first example that people studied in the context of HDXs and showing that it has some great HDX property which is needed for agreement testing. Okay, yeah, this construction has been around for a long time, I think at least 75 years. Okay. And I want to emphasize also that if we're interested in the algorithmic aspects of actually getting an algorithm that constructs an agreement tester so you could use it in a PCP, you want to make a family of agreement testers that are bigger and bigger so that you sort of have a knob to tune in your algorithm. And one nice thing about all of these different groups that you use is that the group is parameterized by a finite field. And so if you make the finite field bigger, you make the group bigger, and then that makes the complex bigger. So that's like one reason, sort of a simple reason why it makes sense to look at these sort of linear algebraic type groups where the object is defined over a finite field. Okay, so Coset complexes are supersymmetric, which is one thing that's very nice about them. And in symmetric complexes, instead of defining expansion in a spectral way, or maybe in addition to defining it in a spectral way, you can, or in a topological way, you can also define it in terms of sort of the isoparametric properties of the complex. And by this, what I mean is something like the following. So for instance, here's a fact. This is just a fact about graphs, not a fact about hypergraphs. If I have a graph and it's very symmetric, it's edge transitive, and the diameter of the graph is small, then this graph is a good expander. It has good edge expansion. Okay? And so you should just think of this as small diameter implies good edge expansion. And this is only true for a symmetric graph because, like, for instance, I guess if you have a very asymmetric graph, if you have a very asymmetric graph, like a dumbbell graph, that looks like, I don't know, it has some stuff here, and then it has some stuff here, and then maybe this is a complete complex or some other low diameter, complete graph or some other low diameter graph. If you take two low diameter graphs and link them by a signal edge, you still get a low diameter graph, but it's a terrible expander. So somehow the symmetry is playing a very important role in all of these constructions. Sorry, I don't know if everybody can see this. And so, yeah, there's an analog of this when we're interested in high dimensional expansion, which is like a one level higher version of this type of expansion that says if you're in a hypergraph, say a 3 uniform hypergraph, so there's triangles, if every short loop has small area, meaning it can sort of be filled in by a small number of triangles, then your high dimensional expansion is good. Okay, this is the sort of extent of the definition of high dimensional expansion that I want to give in this talk. Although I can say more formally what this means, maybe if anyone's interested. Yeah.
And this is an extension of the.
Yeah, I think this is what they said in I think this Kaufman Oppenheim paper from like 5 years ago said it this way, and I like thinking of it this way. You can somehow think of this as like if you want like a even more analogous way to write this condition, you could say like, it's sort of like saying every pair of vertices can be filled in, like the gap between them can be filled in by a short path. This is like every short loop can be filled in by a set of triangles that has a small area. Yeah.
Sure. What do you mean by edge transitive graph?
Oh, like there is a group of automorphisms of the graph that sends every edge to every other edge. Maybe it's okay if it's partite, like it can send it sends every edge to every other edge. There's you can exchange, if I pick any two edges, there's an automorphism of the graph that sends my first edge to my second edge. Yeah.
Just to complain.
Yeah.
The second one doesn't need edge transitivity or anything, it seems.
Oh, sorry, this is, I guess I deleted this. I think this whole slide was supposed to be within only the scope of symmetric complexes.
But I mean.
Sorry, this should say like for symmetric complexes.
But this is true in general, right?
Is that true?
No, it's not true.
It's not?
No, you can construct silly counterexamples like this.
Probably like the dumbbell,
But
like this triangle.
you really need you really need more.
Okay.
But you're saying two things, right? I mean, first, it's not even clear that you can fill.
Yes, this is a good point, which I think I was going to put on, in these little bubbles, but yes. So even it's also interesting to forget about, if you don't care about quantitative aspects and you only care about the question of can every loop be filled in, this is saying something about the complex qualitatively, which is that it's simply connected, which is some notion that people care about in topology, where it's like a donut, for example, a torus is not simply connected because it has a hole in it, which can be expressed as saying that there's a sort of loop in a torus that cannot be filled in by solid or the surface of the torus. And so like just like how in a graph, if you don't care about quantitative aspects, you could just say that a graph is connected if and only if the diameter is finite, which means that there's a path between every pair of vertices. Similarly, in a complex where you have triangles, it's sort of the one higher level notion of connectedness that we typically care about is simple connectedness, which means there's no holes. And this has a similar qualitative generalization, which says that if every loop just has finite area, every loop can just be filled in by some number of triangles, then the complex has some connectivity property, namely it's simply connected. Okay? Does this make sense? Okay. So yeah, so in a coset complex, if we recall our fact that short loops have small area implies good expansion, this short loops have small area condition can be expressed basically equivalently in terms of a question about the group presentations of the group that I'm working with. And I'm going to say what that is in the subsequent slides, but I just want to say this for now to sort of prime you that this is the thing that you should think about that connects all the group theory that I'm going to talk about to some of the sort of expansion considerations that I was talking about at the beginning. And yeah, so this connection is through this thing, this object called the Dane function, where if like you can bound this Dane function object for the groups and the subgroups that you started with, you get a corresponding expansion bound for the coset complex that's defined by these groups and subgroups. So what I'm actually going to essentially talk about for the remainder of the talk is this object called a Dane function, or sort of informally talk about it. And I want to emphasize that all of the bounds that we get in this whole process should be independent of the field size. And that's how we're going to get a family of expanders that's sort of growing and growing, but the expansion bounds are not deteriorating. Okay, so now I'm just going to tell you about some group theory. Maybe why I'm going to tell you about this group theory, maybe you're primed for some of the group theory I'm about to tell you about by these definitions that I was making in the previous slides. So yeah, so what we really prove in the paper is some sort of Dane function bound or isoperimetric inequality for the group, which is the symmetric, determinant one matrices over a finite field, really for unipotent subgroups of this group. But in the interest of maybe making things a little simpler and also actually presenting how we thought about this problem, I'm going to present it in terms of something maybe seemingly slightly unrelated, which is like a circuit-based model for this group.
And we should
Yeah.
think of as fixed.
Sorry?
The parameter and we should.
This is a very good question. So I think in the beginning, like when people first started looking at these complexes, they thought of n as fixed and maybe like 3. But for the agreement testing applications, you want, I think n in the end will be fixed or might be slightly super constant. Maybe like, I don't know, it might be like square root log n or something like that. But you sort of are going to end up wanting to take n to be very large in order to get the agreement testing parameters to be good. So you care in the end that the bounds that you get are independent of n in addition to independent of q, so that you can take n to be large enough for the agreement testing.
So like Q will just be your parameter of growth, which
Yeah.
will be the family.
Yeah.
And then will control something like the error or the expansion.
Well,
Where will it come in the,
it's a
the
good
quality
question.
of the agreement test?
Okay, secretly, yeah, I think n comes in. Well, n will, for instance, govern how large the sets are in the agreement test. Like in terms of like n, I think there's n.
Maybe you
Sorry,
can use
what is the uniformity? Yeah, maybe I can use k, or I might use k for something else later.
ends up
Yeah,
all-
Yeah, exactly. Yeah. There's like
Yeah.
n or n plus 1
He said
subgroups.
that n
Yeah.
is the square root log n.
Yeah, that's.
Oh, sorry. I confused myself. Maybe there's 2 n's. Yeah. Okay.
So the dimension of the complex is governed by n?
The dimension of this complex is literally n, but maybe.
But then you talked about
Yeah, sorry.
triangles, right?
Maybe I should not have said that. I think that, well, in the end, you may be instantiating this entire construction inside a PCP if you want to get PCPs. And then I think that they end up needing to take n to be slightly super constant. But for now, we can just think of n as constant. And yeah, even if n is constant, the number of triangles still grows if you increase the field size. Maybe it will make more sense also when I just tell you the actual sort of alternative way we think about this problem instead of thinking about the complex directly. So, okay. The way I'm going to tell you about this problem is through some lens of circuits. And okay, here's an example of a circuit. This is like a very restricted model of circuit. And these are going to be circuits where you have gates, and I want to read the gates from left to right. And each gate just takes, you use some wires. sorry, I should say this first. You have some wires, and each wire holds a field element on it. And what a gate does is takes the current element on one of the wires and then multiplies it by some multiplier or weight, and then adds the result onto another wire. And for instance, this first gate, this is
You're thinking of the matrix group
Exactly.
with its action on vector.
exactly. And this is just because what we end up caring about is sort of you care about the case where the matrices are really sparse. And if you're thinking of n as like a very large constant, this is like a graphical representation for what the matrices are doing. And yeah, so for instance, this first gate, as Avi says, is just acting on vectors by taking the 0th coordinate of the vector, multiplying it by something, and adding it onto the first coordinate of the vector. Okay, so this is like a sort of ad hoc model that I find useful for thinking about matrices over a finite field, but there's other ways you could think. Sorry.
No, this is Gaussian.
Yeah, this is exactly Gaussian elimination.
Right, so this
Yeah.
is Gaussian, like,
With function, with some coefficient.
Exactly.
No.
Yeah.
Or
Yeah.
no.
sorry,
yeah.
this is like when you write plus f.
Yes.
And then you kind of go down
Yes.
or up to
Yes.
some other. So this is like
Here, I have the matrix here. So this gate corresponds to this matrix,
wait a second.
which says, sorry, this unfortunate fact is that I reversed the order so that the circuits are read left to right, but the matrices
Right, but you're
multiply
you're
right to left.
multiplying
But
right to left. But this is saying like take the first row, which is row 0 of
Yeah.
the index.
Yeah.
Multiply it by f,
Yeah.
add it to the second row, which is indexed by 1.
exactly. Yeah.
And when you write it like this, you're saying this is the order that I do like the elementary.
Yeah, exactly. Exactly.
Okay.
Yeah. And yeah, if you don't want to think about circuits, you could also think about these as programs where you sort of have some registers, and each register holds a field element, and then each gate takes the value of one register, multiplies it by a field element, and then adds the result into another register. And by the way, I should emphasize that because in the end, we're only going to consider sort of the local picture because we want to prove some local expansion bound, which will then be plugged into a bunch of other implications to get the global expansion bound. We're only going to look, at least for until the very end of the talk, at the case where these matrices are upper triangular. In other words, the wire that you're using as your input is above in the picture or numerically smaller than the wire that you're using as your output, which is what it means to be upper triangular. Like all the gates go downward. Okay.
So the arrow, just
Yeah.
pictorially connect the vertical line.
Yes.
You want to put an arrow in what direction? Like, where does the data go? It goes,
It goes down.
goes down.
Yeah, sorry. This is like maybe or, I don't know, Ryan likes drawing these pictures because they look a little bit like quantum circuits or something. Like this is really supposed to be a plus sign saying take whatever's on wire 0 and then plus it onto wire 1, but then there's also some multiplier
Write
weight.
it down on wire
Yes.
1.
Yes, or
Yeah.
increment wire 1 by wire 0.
You add
Yeah.
Doesn't that contradict?
Oh,
what
sorry, I may
think?
have, maybe these should be lower triangular
I
matrices.
think they should be.
Oh, that's my bad.
Alright.
Yeah, sorry.
Or even better, just do it from the right.
You add the zeros row with the coefficient to the first row.
Yeah, but in
Oh, sorry, I should have made
Yeah.
transposed these. That's my bad.
Yeah.
it's okay.
Sorry.
It's okay.
Yeah.
It's just
Yeah, no one has, I've given this talk several times and no one has pointed that out before, so I guess you're paying attention.
No, right.
Well,
Like, are
yeah.
people actually multiplying the matrices now? Like I just kind of believe.
No, but if you look at this matrix, you can see that it actually probably adds the second row onto the first row, not the first row onto the second row.
Well, it depends
If you multiply on the right. Yeah,
Right,
maybe I
right,
should
right.
say that the whole time I've been thinking about multiplying on the left,
But
which is
it's
not
adding
true.
the first column to the never mind.
Yeah, anyhow. Okay, so let me keep
You
going.
can go over time since
Yeah,
our questions are.
Okay. So these circuits, we should think of each circuit as encoding like a potentially very long, if there are many gates, product of these elementary matrices, elementary upper triangular matrices. In particular, every circuit just computes some linear map from a vector of field elements to a vector of field elements. And I'm going to say two circuits are equivalent if they have the same functionality. So if I put in the same field elements, I get the same field elements. Okay, so if you want to think of these as products of matrices, it's like saying that these two circuits are just factorizations of the same underlying upper triangular matrix with ones on the diagonal.
Why is it a +1?
Sorry, sorry, because I annoyingly am calling n2 and then I have 3 wires because I go 0, 1, and 2. I don't know why I decided to do that. I think there was some reason along
So your special linear group is also n+1?
Maybe n+1. Yeah, I was not being very careful about that. Okay, and I'm going to just say that a circuit is trivial if when you expand out the circuit and you multiply out the matrix, you get the identity matrix. Or in other words, it is equivalent to the circuit that has no gates in it. Okay, and the problem that you're interested in, if you ultimately want to prove expansion bounds for these Coset complexes, is in some sense how to certify that a circuit is trivial. Like if I tell you that a circuit is trivial, it multiplies out to the identity matrix. How do you certify that in a certain sense? And I'm going to tell you what that sense is. Okay, so here's an example of of how 2 circuits can be equivalent. So for instance, take this circuit, which is in the top left, which does this plus f plus g minus f minus g. It's 4 gates. For instance, if you take this vector v0, v1, v2, and you plug it into the circuit on the left, this plus f adds v0 times f onto v1. Then you multiply this by g and add it onto v2. Then you subtract f times v0 and from v1, and then you subtract g times v1 from this long expression, and what you end up getting is this vector on the right, which is the same as if I had just had a single gate that took the contents of wire 0, multiplied it by f times g, and then added the result onto wire 2. Okay, so this is like this 4 matrix product is equal to a single elementary matrix. Okay, and this is an example of how there are maybe interesting things that are going on when I'm saying that 2 circuits are really equivalent. And yeah, you can view this as like a fact also about Gaussian elimination if you would like. Like you could do 4 elementary operations and just really be doing a different elementary operation.
Also, you can be thinking you're doing addition, but you're really doing multiplication.
Yes, so somehow, yeah, this is really doing a multiplication of the underlying field elements, which is important, I think, in the end. Yeah. Okay, so here's the particular model that we're interested in when we talk about certifying that certain circuits are trivial, okay? It's going to be slightly artificial, but maybe later at the end of the talk, I'll convince you why this is the model that we end up having to care about. So, okay, so I'm going to say a barrier is just a gap between consecutive wires. So there's a bunch of wires, n+1 wires. A barrier is going to be, I look at 2 consecutive wires and I look at the space in between them. And I'm going to say that if B is a barrier, that a B region of the circuit is just some subcircuit that does not cross that barrier, okay? So for instance, here's a circuit, here's a barrier, it's this purple shaded region, and like these first 2 gates are next to each other and neither of them cross this purple shaded region. So I'm going to say that this is neither of them cross this purple shaded barrier. So I'm going to say that these 2 gates form a region, okay? And ultimately, the reason why we care about this barrier and region sort of view is that the functionalities of regions form a very large subgroup of the functionalities of all circuits, or of the group of upper triangular matrices. So when we're designing a Coset complex, it will end up being the case that the subgroups that are used in the Coset complex sort of correspond to these regions, to these gates which don't cross certain barriers. And if you want to think of it as a matrix, it will look like, sorry, I try to draw this big. You have like a bunch of 1s on the diagonal, and then these subgroups correspond to like, maybe I have a 0 here, and then I have some coefficients here, and I also have some coefficients here. That's what this restriction would mean in terms of matrices.
So you have another region of the middle, right?
Yes, this is a great point. So there can be multiple regions. And sorry, maybe I'll just say here, yeah, you're right. So a single gate might avoid many different barriers. So it maybe is in many different regions, and there are different potential sort of decompositions that you could be doing if you're trying to look at how to decompose a particular circuit into different regions. So in particular, the model that we're interested in is the following. Say I have a region that avoids crossing a particular barrier. What I'm allowed to do is take this region and replace it by an equivalent region, which also doesn't cross that barrier. So for instance, here's what I wanted. So for instance, here is a circuit. In this case, there are 3 barriers. And I have these F and P gates, which both don't cross the purple barrier. So what I'm allowed to do is replace them by an equivalent set of gates that also doesn't cross the purple barrier. For instance, this F and P gates commute. So I can just swap them. And because the original circuit doesn't cross the purple barrier and the new circuit also doesn't cross the purple barrier or sub-circuit, this is an allowed move. And yeah, so there may be multiple barriers, and therefore at any point there might be many different sorts of types of moves that you can do, where you say, oh, I'm going to use this barrier. I'm going to find some gates that avoid this barrier, and I'm going to swap them for some other gates that avoid this barrier. So there might be many different types of sort of reductions that you could try to do when you're trying to certify these trivialities. Yeah.
But if you do this, it will mess up with other barriers, right?
This may be true. Yes.
Okay.
So again, I think the thing to keep in mind is that in the end, you have a circuit that's just trivial in the sense that when you multiply everything together, it actually is, you get the identity matrix. So the interesting question is, can you certify that you get the identity matrix via some process that's sort of more local than just multiplying all the matrices together? And the particular process that you end up being interested in that ends up being equivalent to expansion of the complex is if you're only allowed to do these sort of local, you can't multiply everything out. You can only sort of multiply out and swap around things that are within a particular region, like they don't cross one of the barriers.
Sorry, so
Yeah.
this is a definition, right?
Yeah.
Like for every barrier V, you have a bunch of operations which you call B-reason transformations,
Yeah.
which allow you to replace one circuit with another circuit as long as it's like
Yeah.
consecutive parts
Yes.
that do not cross the barrier.
Yes. So this is in secret something like exactly the same as the Dane function of the underlying group, but I didn't want to define what that is. And anyhow, I find this graphical way of looking at it more helpful for doing the actual bounds. So yeah, and in the end, we're mostly going to be interested in the case where you have a two-dimensional complex. It's just triangles. This is like the smallest dimension in which these expansion questions are interesting. And so for triangles, we want three subgroups. So we consider the case where we have three barriers. And the minimum case then is 4 wires. So you can have like one barrier between each consecutive pair of wires.
And another question,
Yeah.
maybe it regards the image, so maybe it's
Yeah.
not the, but you kind of drew 3 barriers,
Yes.
but everything crosses the first one, like ever, right?
No, in this image, yes, but you
Oh,
could have another
You
one.
can
where
also
that's
have
not
things
true.
that start
Yeah,
from
yeah,
zero.
exactly.
Okay.
Yeah, and I'll have some more pictures, I think, as we go.
Meaning you go below the barrier as opposed to.
Yes, exactly. This is true. Yes. So, yeah, so here's an example of how these transformations that I've been talking about can actually be quite non-trivial. So here's a lemma. So this circuit, which is, look at it, it's a trivial circuit because these P gates use a disjoint set of wires from these Q gates. So they just cancel each other out. But collectively, these 4 gates cross all 3 barriers. So it's not you're not allowed to just say like, oh, these all should just cancel out. You're trying to certify this via some more local transformations that respect the not crossing of barriers. Yeah.
Oh, so when you define cross,
Yes.
You keep the wire you don't preview the wires. Like for example, let me see. So if
exchange 2 and 1, then it would be.
Yes, this is true. Yeah.
okay, so there is topological order.
Yeah, exactly. Yeah, that's a very good point. Yeah. And all of these complexes that people study in this context, this is true. There's some ordering on the different sort of parts that ends up being important.
Okay.
Yeah. And so this was proven like 25 years ago in an algebra paper that there's something that you can do to sort of reduce this to the empty circuit using only these local operations. Here's a simplified proof that Ryan found last year. You can do things like, for instance, take this Q gate and expand it into 4 gates that also don't, like this Q gate doesn't cross the green barrier, so these 4 gates also shouldn't cross the green barrier. So you can do things like this. And one thing I just want to point out is that I have some 1/2s appearing. So this proof does not make sense when the characteristic of the field is not 2. And somehow magically you can do some series of transformations and get the identity circuit, but this is sort of magical. And in fact, we know that this is not possible when the characteristic of the field is 2. So somehow there are some non-trivial things that are happening when you're trying to understand whether you can certify triviality or not by using these local transformations. And okay, so in general, we're interested in the question of, given any circuit, promise that the circuit is trivial, can you make it into an empty circuit just using these local transformations?
Sorry,
Yeah.
about the characteristic.
Yeah.
So both the original proof from 2000 and your proof?
Yeah, and I think in this original proof, they constructed an example in characteristic 2. I'm not sure if they have every characteristic field 2 or only every field of characteristic 2, but I think there's at least a field of characteristic 2 for which this proof does not work. Which there's a counterexample, like you can do this by constructing a larger group which still satisfies all of the sort of relations that you assumed, but which is not actually SLN or SLN plus 1. Yeah, you can construct a counterexample. Yeah.
This policy is not linear in C.
It may be quadratic in C, I think. Because it will end
This
up.
corresponds to the then function
Yeah.
being policy.
Yes, it does. Although I think it's also can be confusing sometimes because maybe there's slightly different versions of the Dane function and maybe there's constant or linear differences that we sometimes ignore, I think, which is part of why I didn't want to define it formally. Yeah, so when we're now thinking about, given an arbitrary circuit, promise that the circuit is trivial, like when you expand it and then multiply all the matrices together, you get the identity matrix, and also the characteristic of the field is not 2, can you certify that the circuit is trivial using only these local transformations? And I want to point out that since we're talking about these local region transformations that never sort of cross barriers that were not already crossed, we should always assume that the circuit we start with has no gates which cross all of the barriers. Because if there's a gate which crosses all the barriers, then you can't really eliminate it using these non-crossing transformations. So what Biss and Dasgupta proved 25 years ago was that if you have 4 wires, which is the simplest case, you have 3 barriers and 4 wires, this is the case I've been showing, and you start out with any trivial circuit and the characteristic of the field is not 2, then you can reduce it down to the empty circuit using a polynomial number of transformations. And the important thing here for us is that this polynomial is independent of the field. So the only assumption on the field is that the characteristic is not 2. And in the application for expansion, at least if you don't care about how good the bounds are that you get, the fact that this is polynomial doesn't even matter. All that you care about is that for some fixed circuit length, there is a constant independent of the field size which bounds the number of transformations that you need.
But you don't have here the condition that you don't have
Sorry.
something that crosses all the boundary, all the.
Yeah. Well, when we have like this type of theorem that says every circuit can be certified, it should have something that doesn't cross all of the boundaries. Otherwise, this doesn't make sense.
Okay. You have,
Yeah.
okay.
You know, this has this thing to do with the bounded generation.
Yeah. So actually,
It seems very similar.
yeah, this is a great point. So okay.
Maybe I should say bounded generation is a property that Yehuda Shalom introduced in order to prove Kashdan property T, so proving expansion.
So by bounded generation, you literally mean that the group can be written as like it's generated by the subgroups and how many elements do you need?
How many?
Yeah, this is a great point. So if you think about this complex as a graph, and you're interested in the expansion, just the usual expansion as a graph, the diameter of the complex is exactly the same as like this bounded generation number, like the maximum number of elements that you need in the subgroups to express the any element of the group. And then when you are using a theorem like this, which is secretly using this Cohn's method, this small area sort of condition, the actual circuit size that you end up plugging in will just be something like twice the length of this bounded generation length, twice the diameter.
Bounded generation is the
Yeah.
length of the words,
Yeah,
Yeah.
the length of
not
the
the
word.
number of generators.
No,
Yeah.
the length of the word.
What were they after in that paper? I'm just curious.
This was a math paper, and they were like, we're after minimal presentations of SLN.
Presentation.
Yeah, so this is all about Dane functions. And well, they weren't even interested in the Dane function. They were just interested in if you're interested in SLN and you want as small a set of sort of operations that you're allowed to use as possible, can you still certify, well, in my language, certify every circuit using this very small set of operations? Yeah. And I should point out, and this is sort of related to what some people have said also, that if you don't care about quantitative things, that you don't care about that this is a polynomial, if you just are interested in, every trivial circuit can be certified by some number of transformations, I don't care about how many, this is equivalent to something like the simple connectedness of the underlying Coset complex. So there's qualitative and quantitative versions of all of these different considerations. And yeah, Ryan found this old picture of Biss and Dasgupta from when they were grad students. And funnily enough, Daniel Biss is now the mayor of Evanston, Illinois, and is running for Congress, which I think is very funny. Okay, anyhow, so one unfortunate fact is that when we actually consider the Coset complexes that we need to study in order to get expansion, what ends up happening is we study a certain variant of the model I presented before. And this variant has that instead of wires carrying field elements, they carry polynomials with coefficients in the field. Okay. And I'm not going to dwell on this because it just makes things more annoying and you can sort of mostly forget about it. But I just want to say on this slide what ends up happening. So you have now wires carrying polynomials and you also have gates, but now the multiplier, which is in a gate, has a constraint, which is that the degree of this multiplier is at most the height of the gate, where the height is like literally the difference between the input wire and the output wire. So I'll show you what this means in a second. But Kaufman and Oppenheim in this paper 5 years ago showed that in the same model, except that now you allow the wires to carry polynomials instead of field elements, you get a similar bound. You have polynomial independent of the field size number of transformations that you need to certify any circuit. And so this constraint makes things more annoying, which maybe Tom knows if you were also thinking about these sorts of things. So for instance, like here's n equals 3 case, and here's a gate which goes from wire 0 to wire 2. So the constraint in this case says that wire 0 is carrying a polynomial, wire 2 is carrying a polynomial, and the degree of this polynomial p has to be at most 2. Okay, so one thing which you do when you want to use these region transformations is like, oh, I would like to take this gate, which is big, and express it as like a product of smaller gates or as a circuit consisting of gates that are sort of closer together. So for instance, I have this polynomial, single polynomial gate, and then I replace it with these 4 polynomial gates. Except now this is not allowed because a fact about polynomials is that not every quadratic polynomial is linear. In fact, not every quadratic polynomial is a product of linear polynomials. So you have to do more annoying things, like you have to start expanding things in terms of separating the different terms in terms of their degree. Okay, this makes things more annoying and we can mostly forget about it. But this ends up mattering in the end if you want to get a growing family of complexes. Okay, so the main theorem that we prove in our work, which ends up all the way downstream, implying like agreement testing and PCP properties of these Coset complexes, is the following. If I start out now in relation to Avi's question, we're now not thinking of n as 3, we're thinking of n as some very large constant. And we're also going to need a condition on these barriers. We're going to need that the barriers are sufficiently far apart. So in fact, we want there's n wires and we want the barriers to be spread out order n sort of amount between them. And I'll say a little bit about why this makes sense.
Fixed constant number.
Yeah, fixed constant. Yeah, it's 3 barriers still. Yeah. Because in the end, you're going to end up wanting to study sort of tripartite complexes, and then using arguments in their papers, you sort of boost this all the way up to getting some agreement testing bounds for the entire complex. Yeah. So if I have, this is our theorem. So if I have a circuit, and this is a trivial circuit, and it's partitionable into L regions, then you can certify it using a number of transformations, which is a polynomial in the number of regions, and also this sort of constant parameter saying how separated the different barriers are. And in particular, all we're going to really need is that for fixed separation and for fixed length, you get some bound which is independent of both the number of wires and of the field size. This is what that's
independent of C as well.
And independent of C, yeah. Well, I guess the L is the length of C. Or like the number of regions used in C.
Okay.
Yeah.
Sorry, it's the length.
Okay, well, the reason I have to say the number of regions is because like when you end up actually looking at the Coset complex, the correspondence is not between gates and group elements, it's between regions and group elements. Because really, you end up, like the Coset complex is defined using groups of matrices. And so you could maybe multiply many matrices together and get a single matrix, and that matrix is like one element.
What happens in a region you collapse?
Yeah, you sort of really should think of the region as like a giant group element consisting of
Subgroup.
a subgroup element.
Region corresponds to a
Yeah,
subgroup.
region corresponds to a subgroup and the entire circuit corresponds to the original group. Yeah. Yeah, and I should point out that like each region might contain many gates, like maybe n squared gates, because if I, have a single barrier, then there's like n squared over 4, gates that are just above the barrier and n squared over 4, I think the barrier's in the middle, below the barrier. So you end up needing, to deal with this problem, which is you might have many, many gates, a growing number of gates if n is growing. But these transformations can also deal with, maybe order n squared or something gates at a time. So you're sort of now playing a different game where you care about the dependence on n. You have these huge input circuits, but then you can also do these very huge transformations. And
yeah, bothers me. Can
Yeah.
you show the layout?
Sorry, go back.
Well, it's just a picture which was anyway.
Yeah.
In the, because I know the process complex.
Yeah.
It's they are cyclic. Here you have a linear order. So it's n+1 because you are wrapping it as 3 equals
Yeah, this is
0.
a great point. So, okay, all of the analysis that we do here and also that was done in these preceding agreement testing papers is just local analysis, where you're sort of taking a link of a vertex and then maybe you restrict ultimately down to some other types of vertices. And once you take the link of a vertex, it goes from being all the wires arranged in a circle to all the wires arranged in a path. So all of this that I'm talking about is just within the sort of local picture. And I'm going to say a little bit at the end of the talk, depending on how much time I have, about what the global picture looks like, where you then allow sort of the wires to wrap around and you allow gates that go from lower wires back to higher
It
wires.
seems that that's exactly the loop that
Yeah.
you want to
Yeah.
avoid,
Yeah.
it's simply connected.
Yeah.
I'm not sure, but maybe you're right. I don't see that.
I think something like this is true. I'll say a little bit about this maybe later.
No, sorry. What? Like, the loop of wires is an artifact of this specific group, and like what's going on here.
Well-
I don't think it has to deal with being simply connected or not, because you could have objects where this analogy still holds for a loop of wires, and they will be simply connected.
Okay, maybe what I said,
Over a finite field. It's something completely different.
well, it's not, I don't think it's, maybe I don't understand correctly, but in my understanding, it's somewhat different. Sorry, it's somewhat related because once you allow the wires to loop around, I'll have a slide at the end of the talk that sort of shows this too. Once you allow the wires to loop around, then you allow arbitrarily high degree polynomials.
No, that's fine.
Yes, but once you allow arbitrarily high degree polynomials, the KO complex is defined by quotienting by irreducibles.
Oh,
And then so somehow this is a reason that the KO complex has covers.
right, but like this is just for this specific
Yeah, that may be true.
setup.
Yeah,
Like
yeah.
there are other setups
Yeah,
where you can find things that you can still describe this analogy, but
Yeah.
things are in a loop and yet you are still simply connected.
that may
So
be true. It's not just that there's a loop, but I think the loop is at least related to this.
Like
Yeah.
Okay, maybe this is a discussion.
Oh, also in the LSB complex, you get that feeling that.
But like also in the LSB complex, if you look at the universal cover, which is simply connected, you can also, like it's also a circle, like a cycle complex in this notion, even though it is simply connected. Like there is not a relation between the graph that kind of models the wire here and the fact that there exist or don't exist loops that you cannot feel. It's just
Anyway, the loop you are covering is horizontal, not vertical. You are covering the word. I mean, you are given a word and you are simplifying it, right? It has nothing to this. I mean,
No, I was talking about this loop.
I know, but this loop, I don't see it related to the loop you are covering with triangle.
Okay, let's.
Yeah, let's talk later.
let's continue.
Okay. Yeah, so I just want to say a little bit about how the proof actually goes. So one thing I want to point out is like on the previous slide, I have this assumption that the barriers are far apart. And I want to give some intuition for why this is a helpful assumption. So for instance, consider this circuit. The circuit's again trivial, but now I have more space between the green and yellow barrier and between the yellow and purple barrier. Okay, this is super helpful when you're trying to do these certification proofs, because you can do things like, if these barriers are big enough, you can expand some of these gates into subcircuits of gates where all the gates are using disjoint sets of wires. And then everything just sort of slides past each other nicely. And maybe this picture also looked more annoying, but it's actually very simple. Like when in particular, you don't, for instance, have to write down the element 1/2. So this proof works in any field, not just fields of characteristic not 2. And I think there's a nice sort of computer science analogy here, which is like you can almost view these gaps between these barriers as like working space or something like that. And then having larger gaps is saying that you have sort of more spaces or more registers where you can like write down intermediate results of the computations that like aren't conflicting with each other. And somehow this is part of why I like drawing these things as circuits. It gives very good intuition for why you could hope to get something sort of useful out of having these larger sort of barriers.
Can you continue? Like, can you continue this like circuit analogy to the other types of complex, like CD one?
This is a great question. You can do something, but the action of the gates is not going to be as clear. And there are also like more annoyances, like if you want to commute 2 gates together, in this case, like the commutator of 2 gates is maybe at most one other gate. Like in those cases, there may be multiple gates that are created when you so somehow you can do something, but it's not as clean as this. I think this is the best case. Yeah.
I think this, you're dealing the whole way through with circuits computing a linear transformation by linear gate.
Yes.
It's in particular here, it's a well-known open problem that we don't know if to compute a particular linear transformation like FT or whatever, whether it helps to have extra space or not, extra registers or not.
I see.
Whether Gaussian elimination is enough, or having extra registers will save you.
I see. Interesting. I don't know.
That's
Okay.
okay. Even existentially, even for
Can you replace the FFT matrix and add some more?
FFT matrix is a product of elementary matrices. We know how to do it in analog n. The FFT algorithm is in place, doesn't need extra memory.
But the extra space would just be more dimensions.
Yeah, or think of a circuit. You have n inputs, and then you have some 5n.
Okay.
5n, gates floating around, and you eventually have the FFT in linear. We don't know.
All right. I just want to say a little bit more about how this proof goes, because I think it's a little interesting. So here's a folklore theorem, which is just a fact about Gaussian elimination, but here written again in terms of circuits. So if I pick any ordering of potential shapes of gates, meaning like pairs where I have a head and a tail and the head is above the tail, then every circuit is just equivalent to a unique circuit where the gates are in this order. So pictorially, for instance, for n equals 3, there are like 6 possible types of gates, which is like the same as saying 6 possible types of elementary matrices for n equals 3. These are 4x4 matrices. And any circuit or any matrix can be expressed uniquely as a product of gates, or as a sequence of gates, or a product of elementary matrices in any particular order. So like fix the order of the 6 types of matrices. Any matrix can be written uniquely as a product of 6 elementary matrices in that particular order. Okay.
Any invertible matrix.
Any invertible. Yeah. Sorry. I'm only ever talking about upper triangular matrices. Yeah.
This is assuming the elements are field, or
this works both for the field case and the polynomial over a field case.
Where it's also a field. With the polynomial.
It's a ring.
It's a ring.
Yeah.
It's a ring.
A bigger field.
It's a ring.
Oh, well, if it's upper triangular, then you think of it kind of. It is.
Well, we are talking about the entries or the.
That's what I thought.
The entries are a field.
Why?
Oh, if you want to think, you can. Okay. I usually think about it as a ring. In the end, when you make the gate circular, so you allow because there's a restriction that the degree of this polynomial f, for example, is degree at most 1. And like there are these degree restrictions. But when you end up moving to the case where the gates are sort of arranged in a circle, and I have a picture of that at the end, then, and you allow the gates to wrap around, you can get arbitrarily high degree polynomials. And that's when you quotient by an irreducible, and then you're back to the case where you have a finite field.
Yeah.
Yeah. But this I think you should think of as a ring because it's sort of just the upper triangular case. Yeah. Okay, so a fact, which is that if C is trivial, meaning I multiply all the elementary matrices together, I get the identity matrix, then if I put the circuit in a normal form where I like arrange the gates in some fixed order, all of these different coefficients on all the different gates have to be 0. This is just by uniqueness. Like in particular, when all the gates are 0, when all these weights are 0, it is equivalent to the identity matrix and it's unique. So essentially, when you want to certify triviality of an arbitrary circuit, what you want to do is take the circuit and sort of put it in order, because once it's in order, everything has to be zeros and you just have the empty circuit. So you can think of this as almost like a sorting operation, except it has the annoying property that sometimes you can't actually just swap two adjacent things. When you swap them, it might, if they don't commute, it might sort of create an additional gate. But if you do this in the right order, like the gate heights that you're creating are getting higher and higher, and this process will still sort of terminate quickly. So like, I don't know, in this case, you swap the -2 and the +3, but you created this +6 gate where 6 is the product of, maybe negated product of -2 and 3. And then you have to do some swapping and you end up swapping and you're happy because now you got a circuit which is in the right order. Yeah.
So each time you will select a region and then perform the equivalent transformation.
Yes.
So I wonder when you will select the region for the middle bar.
This is a good question. Because you end up almost always caring only about the top bar and the bottom bar. But for instance, like this proof that I had here, you do, for instance, like here you want to swap this +p, which only crosses the green, and this -1, which only crosses the purple. And you can only do that because neither of them cross the yellow. So sometimes you end up needing this, but you end up using it less, I think, than the other two.
But the gates you add will not cross the middle bar as well, right? Like you are not allowing to.
No, sorry. Every gate has to not cross at least one bar. But for instance, if you have like this, I guess this is a good point. If you
So this region right now is the middle region, like the yellow region.
Yeah.
And what is allowed transformation here?
You can swap this +p and this -1. You can commute.
But that will require you to make a big gate, like go cross.
No. These just commute.
Oh.
They use disjoint sets of wires. So the only case where they don't commute is when the output wire of one is the same as the input wire of the other. Yeah. I have a picture of this maybe on the next slide, so I might just show you. So, okay, let me go back to where I was. Okay, yeah, so in general, the set of sort of local transformations that you need in order to be able to put any circuit in this normal form is the following. It's just like all possible sort of operations that involve only two gates that are next to each other. So for instance, if I have two gates of the exact same type that are right next to each other, I just add the coefficients as equivalent. And if I have, this picture is slightly misleading, but if I have two sets of, if I have two gates that use purely disjoint sets of wires, they commute. And in fact, also, the reason this picture is misleading is because they also commute if, if I have, say, 3 wires, and then I have like one gate that does this, and then I have another gate that does this. So these do not use disjoint sets of wires, but the outputs are, it's not the case that the output of one is the input of the other, which is the bad case where they sort of interfere with each other. And then so the final annoying relation is when the gates don't commute, because indeed the output wire of one gate is the input wire of the other. So you have to then create a third gate if you want to swap the two gates. That explains the sort of interference between the adjacent gates. Okay. So the proof strategy is just you want to implement these sort of pairwise relations called Steinberg relations in this barrier region transformation model. And some relations are themselves already just transformations that are allowed in this model, but we're missing some relations where the gates in the relation cross all three barriers. So for instance, this is a relation in the n=3 case, and this P gate crosses the first two barriers, and this Q gate crosses the second two. So you need to do something, oh, sorry, the equality sign showed up in the wrong place, but you need to do something non-trivial to implement this as a series of transformations. But I already showed how to do that earlier in the talk, so this is not hopeless. And one particular annoying issue is that some of these relations, like for instance, if you had like one gate sort of here where my pointer is, and then another gate where this pointer is, this relation would end up involving a gate going from, in this case, wire 0 to wire 3, if you want to commute them. But I've named, like these gates do not exist in the model that we're actually looking at, in the sense that like we're interested in certifying trivial circuits, but we already assumed at the very beginning that the circuits don't have any gates that cross all the barriers. So if such a gate arises, it sort of doesn't exist within our model, and you have to like make some alias for this gate because it doesn't really exist and treat it as like some equivalent subcircuit. There's like a bunch of annoying things that start happening when you try to actually carry out this strategy.
You mean that this new circuit arose when you did some transformation?
Yeah, well, it's like, okay, you want to put a circuit in normal form, except this normal form will include these gates that don't actually exist within the model. So you have to come up with some alias, and then every time you want to refer to this gate, actually refer to this gate. And it's somehow annoying because there's many different aliases, and you end up having to show that they're all equivalent.
Doesn't it ruin the uniqueness?
Sorry.
Doesn't it ruin uniqueness?
No, because well, if you come up with a unique, like if like you can literally think as if the proof contained these gates, but then every time you write this gate, actually write this series of gates.
And then you can write them presumably in more than one way.
Yeah, but
No, but we're-
that somehow doesn't matter because we're just using it as an artifact of the proof. So like you could think as if you did the proof involving these gates, but then every step where you used this gate, you actually use this subcircuit of gates.
And so you change the ordering that you promised in the canonical order.
This is true, but somehow doesn't matter in the sense that like, I really think of it as like the real proof involves this, but then you replace every one of these gates with one of these subcircuits. And so at the end, if the Z is 0, you get like another subcircuit with these Z's being 0, which is also a trivial circuit.
Like,
There's something to prove.
there is this uniqueness theorem.
Yeah.
It's a theorem, right? Like,
Yeah.
it doesn't matter if we don't need to.
Well, but the uniqueness theorem contains
No.
such gates.
Right. It contains this last gate.
Yeah.
You can derive a uniqueness corollary saying that you can always write things in the order that you like, except that
Yeah.
when you, instead of having this 0 to 3 gate, you replace it by what we agreed upon, which is this 0, 2, 2, 3, 0, 2, 2, 3
Which
gate
gets
of
things
this
out
exact
of
form.
order.
Because these
Which
two,
got things out of order.
Right,
no,
but that's like
but
your
But
new
you're-
canonical form.
this is your new canonical form. It is not in the order that we said before. And because this kind of violates that, but except for that, everything is.
Well, except that this happens quite a number of times in
No.
the construction.
There is no construction. It's just a uniqueness theorem. Like every circuit you can write in this form. Corollary, every circuit you can write in this form where instead of 0 to 3, you put these specific 4 gates and it's unique. And this is also unique.
Yeah.
Now I like the problem, if I understand.
Yes.
Maybe I don't understand.
Yes.
Like if I understand correctly, the problem is that you want to use this now constructively.
Yes. And there's other problems. For instance, if Z is high degree because these are polynomials, then like you want this circuit is going to need more than 4 gates, but you want it to have a small number of gates so that you're not blowing up the complexity. It's annoying, but These are the sorts of annoyances that you have to deal with in the proof.
You want to say that this thing converted somehow.
Yeah. But okay, at a very high level, the idea of the proof is just the following. So we think of having a circuit, except that this is a circuit originally that had like a growing number of wires, n wires. But now we're going to block sort of all the circuits, all the wires together that were sort of in between an adjacent pair of barriers, or like above the first barrier or below the bottom barrier. So this sort of makes your original circuit look like a circuit, except now each wire corresponds to like a bundle of wires in the original circuit, and all the matrices become block matrices. Like you think of the wires as becoming carrying vectors of polynomials instead of just polynomials, and you think of the gates as the weight is now a matrix instead of just a single sort of scalar value. And so somehow you want to carry out the proof that we did before for the constant size case, except with all of the inputs and outputs being block matrices and block sort of vectors instead of just vectors and scalars.
Even that is not, it's not easier to just formulate everything in the original group theoretic.
Well, okay, the reason that it's not, because you have to deal with this annoying issue of the fact that these are polynomials and there's constraints on the degree of the polynomials.
Yeah, but
So I think, okay, let me think for a second. Okay, I think it is not clear how to do this, but well, one reason is that these matrices may have different sizes, and
You mean the different blocks?
yeah, like different block sizes. And
why should they?
well, it's because the barriers are not like equally separated. They're just like some linear separation. So these numbers might actually be different in terms of how long this vector is and how long this. So the matrices are like rectangular.
Can't you really?
Are you choosing the barriers randomly?
Yeah, they'll end up being chosen randomly. So all you can really say is that they're
Are you
far apart. And in the end, when you apply this is all taking place because it's part of a reduction that shows agreement testing from some local expansion condition. And that expansion condition will end up, among other things, taking these barriers randomly. So we can just rely on the fact that they're far apart, like linearly far apart, but not on the distances behaving really nicely better than that. At least as for the argument I know, there may be better arguments now that maybe obviate some of these problems. Okay, can't remember off the top of my head. Okay, it definitely does not work to just be like, I'm going to do the group theory again, but I'm going to do it all with matrices instead of with field elements. But maybe let me think about that offline for a little bit, and then I'll tell you later about why it doesn't work. It's a good
Just
question.
to clarify in my mind, I'm
Yeah.
not going to
Yeah.
argue again
Yeah.
about it. But region means in a subgroup.
Yes, exactly.
No, but
Okay.
even just to say, I mean, once the subgroups are bigger than scalars, what used to commute doesn't commute. And
Sure.
Yeah, okay, this is one good reason. Like these are non-commutative.
Yeah.
Right, I don't know. It definitely doesn't work. I'm trying to remember.
If you work in the group and not in the.
so, I mean, even if he had a proof for the scalar case, it doesn't immediately.
No, multiplication of polynomials is.
Yeah, but multiplication of matrices of polynomials.
Polynomials doesn't.
Yeah, then you could, okay.
That's a good question. So I should come up with a better answer for it. But it doesn't work because this occurred to us originally, and we were very excited about that, and then it ended up being annoying. There's a lot of annoying edge cases because these barriers are just picked randomly, so you can't really control very nicely like how they're arranged. Yeah, anyhow. Maybe I'll just say at the end, I know we're already over time, I'll say a little bit about what the complex is that ends up being studied. So a Coset complex is very simple. All it is I have a group, which you should think of as all circuits, and I have subgroups, which you should think of as the regions. And a Coset complex is a partite complex. It's a partite hypergraph, if you prefer to think about hypergraphs, where basically the hyperedges just correspond to I look at each element of the group and then I make a hyperedge which contains all the different cosets of this group element by all the different subgroups. So if I have three subgroups, then I have a three uniform hypergraph, or like if it's a simplicial complex, then these are the maximal faces of the simplicial complex. And so you sort of think of it, for instance, this is in the case where you have three subgroups, as like each triangle corresponds to a group element and indicates what are the three cosets by the three different subgroups that are sort of incident to this or determined by this group element. And yeah, so there's a bunch of different complexes that you sort of end up having to worry about. So there's the global complex, which is the complex that you actually get when you arrange the wires like in a circle, so to speak, and you deal with matrices that have entries both above and below the diagonal. I'll say a little bit about what this is in a bit, but in the end, the complex we actually care about is the complex that just has like three barriers, and you look at the corresponding complex. So for instance, if you look at, okay, this is the n equals 3 case, but think n is much larger than 3, and there's three barriers, and then you take G, the group that you're using to define the complex, to literally be the group of functionalities of all circuits, which is equivalent to the group of upper triangular matrices, where like there's some restriction on the degrees of the polynomials in the entries, like the diagonal that's one above the main diagonal is linear, and then two above the main diagonal is quadratic, and so on. And then you can make subgroups of this group by just considering these barriers. So for instance, if you look at the circuits that don't cross barrier B1, you get a subgroup. And this is, for instance, this subgroup contains this G and this H and this Q, because none of them cross the green barrier. And you make two other subgroups corresponding to the two other barriers, and then you have a rank 3 coset complex. And this is the entire construction. So it's just like these all correspond to groups of matrices, and you look at the cosets of these matrices in the big group by the subgroups that are determined by these barriers, which correspond to zeroing out certain entries of the matrices, and then you get a complex.
So this lives in SL4.
This example would live in SL4, yeah.
It will be only upper triangle.
It will be only upper triangular. But this is a sort of local version of the entire complex. So then the full local version of the complex is just, instead of only having three barriers, consider all possible barriers. This is still upper triangular, but now it's like an n-dimensional complex if there are n+1 wires. And these arguments, like the arguments in Yotam Manirit's paper and in Doran Mitali's paper, let you sort of reduce from considering this complex with many parts to this complex with only three parts when you want to prove expansion bounds. And then the complex that is the actual KO complex, the glorious final thing that we actually prove the expansion bound for, is as Irit and Avi were saying, is the complex where I also allow circuits that sort of go around from bottom gates to top gates. This is the general SLN group that has lower triangular in addition to upper triangular matrices. This is now, there's no longer like this linear structure on the wire. The structure of all the wires is sort of cyclic, because like in SLN, there's no notion of like what the top entry of the matrix is. You can sort of cyclically permute all the coordinates and you still get a matrix which is an SLN. So for instance, you can do these commutators where you have like a gate and then another gate and then a gate and then another gate. And unlike before, you can now get these subcircuits which are equivalent to single gates, where like you actually have gone from bigger gates that were sort of higher, they like spanned many wires, to gates that spanned few wires. This is just because things sort of wrap around. And the point is that once you allow this, if you allow these, even if these gates that you started with were just linear polynomials, by just iterating this over and over again, you can get polynomials of arbitrary degree. So you now have an infinite group. So you can get, even if F is a finite field, you can get polynomials of arbitrarily high degree by just wrapping around the circle again and again and again. So if you want to get an actual finite complex out of this, what you have to do is take everything we did and take it modulo an irreducible polynomial. And by making this polynomial higher and higher degree, you get a larger and larger complex. And by the way, like as Avi was saying, like if you take the group SLN and if you then look at polynomials but modulo an irreducible polynomial, this is just the same as a larger finite field in the original finite field you started with. So this is how the complex ends up being just parameterized by a finite field. But really it's like there's a single base finite field, which you think of like as FP, and then the complex is defined over like FP to the S, where S is a growing parameter. Okay, and yeah, you should think of this literally as the same as all these circuits that I've been talking about before, except now I allow gates that sort of wrap around circularly. And I have to add an extra barrier between wire N and wire 0. So here between wire 9 and wire 0, there's another barrier. Okay, and I've increased the rank by 1 because I've added an extra barrier. Okay, so the point is that in the end, the thing which we actually have to study is the expansion of this simple tripartite complex, which only has 3 modes, which is what I spent a while telling you about. But via this chain of reductions, and like you read in Yotam's paper, and some other reductions, and you need some other conditions. In particular, you need also a global connectivity cohomology condition about the entire global complex, which is a almost disjoint problem from the problem that we were talking about, which was proven in this Kaufman, Oppenheim, Weinberger paper also from last year. If you put all these things together, you end up getting whatever great HDX condition that you want for this global complex, which is that, as Yotam would call it, that the swap complex of the global KO complex is a co-boundary expander over the symmetric group, or some such thing, which is a mouthful, which is why I've just been calling it a great HDX. And yeah, so that's basically what I wanted to say. So one interesting question that's left from all this is like, as I said, there's this like chain of reductions that you plug in from this local sort of restricted expansion bound that we actually prove to get some final HDX condition for the entire global complex. Be interesting to try to do this via more sort of group theoretic methods instead of passing back and forth between group theory and then the simplicial complex picture, which is sort of annoying. And another sort of very interesting question is, can you get better PCPs in the application, which is the final application of all these agreement testers, by the fact that the KO complex has some nicer properties than this Chapman-Lubotzky complex? So yeah, thank you. That's the talk. And here's, people have been telling me to put QR codes for the archive links at the end of papers. So now I've been doing that. Yeah. Okay. Yeah. Thank you.
Okay, so for questions to lunch.
Yeah.
We're a bit over
Yeah. Thanks for staying over time.